In the last video, we have introduced the concept of electric chiral magnonic resonator. The concept was introduced in a two-dimensional format, where we have considered variation of physical quantities in the x and z direction, but not in the y direction. Effectively, we are considering a system where both the bottom continuous film waveguide and the top stripe resonator extend to infinity in positive and negative y direction. There are no variation of physical quantities along the y direction. However, such treatment remain unsatisfactory because after introducing a third dimension, there is always a possibility of spontaneous symmetry breakage along this new dimension, leading to spin waves traveling in the y direction. This will render our previous assumption of no variation of physical quantities along y direction no longer valid. Another reason that the two-dimensional treatment of electric chiral magnonic resonators remain unsatisfactory is because for useful information processing, one have to form circuitry on a plane. This is true both in electronics and photonics, where information represented as electrons or photons travel on designated path on the plane defined by electric wires or photonics waveguide. Therefore, if one is to develop the concept of magnonics in analogy to electronics and photonics, one would also need to form circuitry on a plane as well, where magnons move on designated path on a plane defined by magnonic waveguide. In such perspective, our previous two-dimensional treatment of electric chiral magnonic resonator is not good enough. The assumption of no variation of physical quantities in y direction is simply incompatible with the idea of magnons traveling in designated path on a plane that can be steered to arbitrary direction on the plane. What we need is to have the electric chiral magnonic resonator interacts with spin wave confined in a magnonic conduit. In another word, we need a model of electric chiral magnonic resonator in the three-dimensional space. When we were in the two-dimensional model where the magnonic waveguide is a continuous film, it is a common practice to apply a bias magnetic field in the y direction. This will align magnetic moment in the film in the same y direction. Spin wave launched and propagates in the x direction are called Damon-Eschbach spin wave. Damon-Eschbach spin wave is very popular among experimentalists because when you look at the dispersion curve of this spin wave, it has a very high group velocity in the long wavelength regime, which implies that Damon-Eschbach spin wave is very easy to launch and be detected. However, if we want to confine spin waves into a narrow conduit, the most straightforward way is to remove magnetism in the area outside the conduit. In other words, magnetic moment will confine themselves inside the conduit region. However, because of demagnetization effect arise from the magnetic bound charges formed at the edge of the conduit, one would need a much larger bias magnetic field to keep the magnetic moment in the same y direction. What if we simply turn off the bias magnetic field? Because of the magnetic shape anisotropy, the magnetic moment inside the conduit will reorient themselves to align with the long axis of the conduit, which is the x direction. Spin waves that travel in the same direction as the magnetic moments are called backward volume spin waves. Backward volume spin waves are less popular with experimentalists because if you look at the dispersion curve in the long wavelength region, the gradient of the dispersion curve is pretty flat. A flat gradient implies low group velocity, which makes it difficult to launch and detect the spin waves. In order to get high group velocity, one has to launch backward volume spin waves in the deep submicron wavelength region. However, short wavelength spin waves are also difficult to excite. However, despite the aforementioned shortcomings, backward volume spin waves does have their advantages. Firstly, it is able to operate without applying any bias field. But more importantly, suppose the magnonic conduit is not straight, but contains some curved sections. When you turn off the bias field, magnetic moments in the straight region of the conduit will align along the conduit long axis, which is the x direction. However, inside the curved region, magnetic moments will follow the local curvature. If you launch spin wave on one side of the magnonic conduit, the spin waves will follow the conduit curved direction in the center region and continue their propagation to the right side of the conduit. This is a very important property of backward volume spin wave as it allows one to steer spin wave to arbitrary direction on a plane determined only by the geometry of the conduit. This serves the basis to form the aforementioned magnonic circuitry on a plane where magnonic information travels in designated path on the plane defined only by the geometry of the magnonic conduit. Okay, we have now established that we need a three-dimensional model of electric chiral magnonic resonator that interact with spin wave in the backward volume geometry. What happened next? If we are still retaining the shape of the resonator as long stripe as in the two-dimensional case, a magnetic resonance will be excited at where the stripe cross with the magnonic conduit. Unfortunately, this resonance won't be local. It will excite spin waves that travel away from the site of resonance. This will increase damping upon the resonance itself. Moreover, suppose we have another stripe resonator plus magnonic conduit sitting next to the first one. Spin wave launched from one resonator will reach the adjacent one through the stripe. In other words, the two resonators are cross-talking with each other, which is undesired. The easiest way to stop spin wave traveling from one resonator to another, of course, is to physically remove the connection between them. To ensure a well-defined magnetization state, we add taper ends to the truncated stripe. Effectively, the resonator becomes a nanomagnet. In fact, when the concept of the so-called chiral magnonic resonator was first introduced back in 2012, the resonators were indeed nanomagnets, which are encircled by the blinking green circles. At that time the term chiral magnonic resonator did not exist, and the device was originally named nanoscale spin wave valve and phase shifter. The idea was to utilize the static magnetization direction of the nanomagnet to either control the magnitude or the phase of spin wave transmitted through the underneath region of the nanomagnet, encircled by the blinking green circles. However, the use of nanomagnet as resonator does come with problems. Suppose we have a nanomagnet lying in the XY plane, with its magnetization pointing in the negative Y direction. The nanomagnet will produce a magnetic field in the surrounding. Now if you place a second nanomagnet next to the first one. Depending on the location of the second nanomagnet, the magnetic field that it experiences from the first nanomagnet will change accordingly. When we design magnonic circuitry, there will be multiple number of resonators sitting in arbitrary positions in the plane. Therefore, each of them will experience a different stray magnetic field strength from the first nanomagnet and be detuned to a different resonance frequency. This would be disastrous for the functioning of the circuitry. On the other hand, a nanomagnet also brings an unexpected problem when we try to electrify it. Suppose we look at the nanomagnet from the side. One may think that in the ground state the magnetic moments inside the nanomagnet lie entirely in the XY plane. Unfortunately, this is not true. In order to minimize magnetostatic energy, magnetic moments at the two ends tilt slightly out of plane. Suppose we add a waveguide below. Also, to electrify the resonator we add a top electrode. Now if we want to parametrically pump the resonator to turn it into an amplifier, we apply an AC voltage at a frequency that is twice of the resonant frequency of the nanomagnet. Since the magnetic moment at the edge is tilted out of plane, it will produce a demagnetization field in the Z direction, which is proportional to the Z component of the magnetic moment. What voltage-controlled magnetic anisotropy does is to alter the proportional constant according to the applied voltage to the top electrode. Therefore, when an AC voltage is applied, the magnitude of the demagnetization field in the Z direction oscillate, and therefore the local magnetic moment at the edges of the nanomagnet oscillate too. This will emit spin waves into the magnonic waveguide underneath, which is disastrous because an amplifier should not produce signal by itself. An amplifier should amplify an existing input signal, but should not produce a signal by itself out of nothing. In order to address all the aforementioned problems we encountered with designing electric chiral magnonic resonator in three-dimensional space, we recently uploaded a paper to a preprint server, where we present a design of electric chiral magnonic resonator base on a magnetic stripe with a localized top electrode. The advantage of such design is that because a stripe does not have physical endings in Y direction. When you zoom in, magnetic moments stay in the XY plane everywhere inside the stripe. Remember, demagnetization field in the Z direction is proportional to mz, which is the Z component of the magnetic moment. If the mz vanishes, then the demagnetization field also vanishes. Therefore, when we apply an AC voltage to the top electrode, the magnetic moment just remains stationary because the demagnetization field in the Z direction remains zero all the time. This fulfills the requirement that without an existing spin wave input, a magnonic amplifier should not emit spin waves by itself. Another advantage of the stripe resonator is that in the remnant state, magnetic moments inside the stripes always align with the long axis of the stripe. This is true even if the stripe has a curved section. Therefore, magnetic bound charges only exist at the endings of the stripe. These bound charges do produce magnetic stray fields. However, if we make the stripes long enough, these stray fields will be too far away from the resonators and therefore affect resonance frequency of the resonators to a minimal extent. This allows the resonance frequency of all the resonators in the circuitry remain the same. This is very important from the perspectives of circuitry design since signals are modulated into a single carrier frequency. If a resonator's resonance frequency is detuned away from this carrier frequency, it will no longer be able to function as a resonator. Okay, what about the aforementioned problem of spin wave traveling from one resonator to another resonator located on the same stripe? Isn't that we don't want resonators to crosstalk with each other? Let us look at the resonator from the negative x direction. When a magnetic moment inside the stripe is set into precession, it will produce demagnetization field Hz, which is proportional to Mz. In this equation, Ms is the saturation magnetization value of the magnetic material of the stripe. Nz is a geometrical constant. In a normal region of the stripe, Nz equals 1. However, in the region where the stripe is covered with the top electrode, because of an interfacial interaction between the magnesium oxide and the magnetic stripe, Nz no longer equal 1, but is reduced by a surface anisotropy term. On the other hand, magnet moments in the stripe precess with an angular frequency omega naught, that is equal to the square root of omega x times omega z, where omega z is equal to gamma times Nz times Ms. Therefore, a smaller Nz will translate into a smaller precession frequency. Now if we plot the precession frequency of magnetic moments across long axis of the stripe, one would find that the frequency is lower in the region that is covered by the magnesium oxide. In physics, frequency is energy. The lower the frequency, the lower the potential energy. Effectively, we have created a potential well of spin waves. Spin waves excited inside the well will be trapped in this well defined by the top electrode and will not propagate to area outside of the well. We put this design of spin wave well into test by running micromagnetic simulations. In the simulation, spin waves are injected from the left into the magnonic waveguide towards right. When the spin waves reach the underneath region of the stripe resonator, the spin waves set the resonator into precession and are being absorbed. Notice that the oscillations in the resonator is confined to area covered by the top electrode and do not propagate to area on the stripe not covered by the top electrode. Since spin waves are being absorbed by the resonator behave as an attenuator, which is symbolized by a resistor symbol. To emphasize that the extent of attenuation can be modified by changing the applied bias voltage on the top electrode, we add an arrow on the top of the resistor symbol, indicating that the attenuator is a variable attenuator. Now, suppose we apply an AC voltage which is large enough to the electrode, then we would obtain an amplifier. Notice that spin wave amplitude at the output from the resonator is larger than those at the input, which implies the resonator indeed is behaving as an amplifier, as symbolized by the usual amplifier symbol in electronics. Now suppose we further increase the magnitude of the applied AC voltage, we will then turn the resonator into a signal generator. In this case, even there is no input spin wave, the resonator is still able to generate an output spin wave. Because the chiral nature of the resonator, emission of spin wave is unidirectional, that is largely only to the right direction. To symbolize the resonator behavior as a signal generator, we borrow the usual symbol for AC current generator to represent the resonator. We add a small arrow under the symbol to emphasize emission of spin wave into the waveguide is unidirectional. Now, if we place an attenuator in tandem with an amplifier, we get a neuron. The transfer characteristic of a neuron is highly nonlinear against incident spin wave amplitude Mz, which consist of a dormant region and a firing region. The details of an ECMR neuron behavior is referred to the reference as indicated in the screen. Now, we have the signal generator which emits spin wave. We have variable attenuator to control amplitude of spin wave signal. We have amplifier to restore amplitude of the attenuated spin waves. We then have the directional coupler to exchange spin wave information with another branch of magnonic waveguide. Lastly, we have the neuron to provide the nonlinear transfer characteristic that is necessary for computation or neuromorphic behavior. Are we ready to construct our ECMR magnonic circuitry? Unfortunately, not quite yet. So far we have ignored the influence of temperature. In micromagnetic simulation, the effect of thermal fluctuation is represented by a random magnetic field BTH. There are a lot of parameters in this expression. At this moment, we just want you to pay attention to delta V, which is the cell volume size in micromagnetic simulation. When we were working with the two-dimensional model, the system is supposed to extend to infinity in the y directions. Therefore a simulation cell is also infinitely long in the y direction, and we can argue that the volume of this cell is infinite. This will suppress the magnitude of the thermal field BTH to 0. Therefore we can ignore thermal fluctuation in the two-dimensional model. However, when we move on to a three-dimensional model, the width of the simulation cell is bound by the width of the waveguide. Therefore we can no longer treat the cell volume as infinite, and we can no longer ignore the thermal random field. If we turn on this thermal random field in the simulation at room temperature, the magnonic waveguide actually looks like this. Therefore, all the spin wave we saw in the previous slides will be submerged in this bath of random thermal spin wave. Okay, what's next? Should we just give up magnonics and move on to something else? The first line of treatment against thermal fluctuation, of course, is to lower the temperature. In this figure, the amplitude of random thermal spin wave is plotted against temperature. Here is where the amplitude stands at room temperature. The red dotted line represents the expected operation amplitude of spin wave in a ECMR magnonic circuitry. As one can see, right now the expected operation spin wave amplitude is submerged below the thermal noise. In order to bring the thermal noise amplitude down to, let's say, 10 times below the operation amplitude, one would have to lower the temperature to 0.1 Kelvin. To bring the temperature to such a low value, one would have to place the magnonic chip inside a cryostat. Such act is totally against the principle of energy economy and spatial miniaturization of modern computing. Moreover, a lot of material parameters, such as magnetic anisotropies, saturation magnetizations, or damping factors modify their values at low temperature. There could even be the complication of superconductivity at the nearby electrodes at such low temperature level. Therefore, low temperature operation implies a whole new subject to be investigated and is out of the scope here at this moment. Another way to improve signal-to-noise ratio, of course, is to raise the signal spin wave amplitude. However, there are also concerns regarding this. Firstly, increasing signal amplitude implies increasing energy consumption of the magnonic circuitry. Secondly, which is even more severe, is the nonlinearity of spin wave. Because of spin wave nonlinearity, a lot of magnonic devices fail to function properly at large spin wave amplitude. Take the attenuator as an example. The transmission amplitude depends heavily on the amplitude of the incoming spin waves. At very small incident spin wave amplitude mz, the attenuator absorbs all the incident spin waves and transmission to the right is next to zero. However, when the incident spin wave amplitude is raised to say slightly larger than 0.02, the attenuator is starting to give way to the incident spin waves. The attenuator is no longer able to absorb the incident spin waves entirely, and there are leakage spin waves to the right side of the attenuator. If we further increase the incident amplitude to 0.035, amplitude of the leakage spin waves to the right side of the attenuator simply becomes even larger. Therefore, if we want to raise the operation amplitude of spin wave to fight against thermal noise, we would need the attenuator to be more resilient against raising spin wave amplitude. Graphically, this would imply stretching the transmission curve to the right side of the graph. This could be achieved by, for example, changing the separation distance between the resonator and the waveguide, or changing the damping factor of the resonator magnetic material. Indeed, to raise the operation amplitude of spin wave requires redesigning the existing electric chiral magnonic resonator, which would be an intense subject in itself. Lastly, if you do not want to go to low temperature, and you don't want to modify the design of your device, there exists a most straightforward solution to the noise problem, that is simply to decrease the operation bandwidth. This is the principle of nearly all experimental results on nanomagnonics in the literature are based on. The idea is very simple. Suppose you have a weak signal that is buried under noise. At a first glance there is no hope of detecting the signal. However, if your signal lasts for a long enough period of time and you add them up together. Suppose similarly you add up all the noise within the same period of time. Because the noise are random with respect to time, they cancel out each other in this sum-up process, while the signals constructively interfere with each other over the same prolonged period of time. You end up recovering the signal with a decent signal-to-noise ratio. Of course, the price to pay for is that it takes a much longer time to obtain the result. That is the reason it is named as decreased operation bandwidth. Now the performance of a magnonic circuitry is given by a figure of merit that is equal to the time it takes for the circuitry to finish a computational task, times the physical area that the circuitry occupies on the chip, times the energy it takes to finish the computational task. The smaller this figure of merit, the better the performance of the circuitry. Now, because of the small bandwidth operation, magnonics scores very bad in the time section. However, magnonics is supposed to score well from the area and energy perspective. Whether magnonics is competitive enough in terms of this figure of merit when compared to other technology is still a topic to debate. Hope that you would be the person to resolve this problem. We are now reaching the end of this video. Please subscribe to this channel and press the like button. If you want to know more about electric chiral magnonic resonators, please click on the link provided in the video description section below for further readings. Thank you again for watching this video. Hope to see you soon in the next video.